Hello. Welcome everybody to the main act of this conference. Thank you very much for coming here to this SQL talk. I'm very happy that the previous show in this room concluded with the slogan, Java is dead. Why is Java dead? Because SQL, ladies and gentlemen. This is a talk, 10 SQL tricks that you didn't think were possible, right? So it is also often referred to as the talk, 10 SQL tricks to convince you that SQL is awesome, or for my American friends in this audience, make SQL great again, right? Why are you here? You're all here because these clickbait headlines, they do work, ladies and gentlemen. So like, for instance, trick number 3, changed work forever. Trick number 8 makes doctors hate you, and trick number 9 is bigger than life. You won't be disappointed tonight. A little bit about myself. I'm Lukas from Zurich. I'm the founder and CEO at Data Geekery, a small company in Zurich. I'm an Oracle Java champion since recently due to my work in the Java SQL ecosystem. And I'm a JUC Switzerland board member, so we organize a lot of talks in the German part of Switzerland. So if you ever come to Zurich, do check out what we're doing. We have a lot of very interesting talks in Zurich. I personally believe that SQL is a device whose mystery is only exceeded by its power, and today you will agree with me on that. Why do I talk about SQL at Java conferences? Because SQL is the only ever successful mainstream and general purpose 4th generation programming language. All the other ones have died. Prolog was great, but no one uses Prolog. All the other languages that do these kind of declarative programming, they're dead, but SQL is still there, and this is awesome. Why doesn't anyone else talk about SQL? I don't know. Who in here uses SQL databases? Everyone does. No one talks about SQL even if everyone uses it. Why is that? I don't know. What is SQL, ladies and gentlemen? SQL is the original microservice. Why is that? Just install a single store procedure in an Oracle Express Edition instance, deploy, and you're done. Right? Okay. Is this SQL? Who in here thinks this is SQL? Yes, you all agree? Why are you shy? Don't be shy. This is SQL, right? That's what you think SQL is. Is this SQL? Who in here writes SQL like this? Yes, you can go forward, it's okay, it's a standard. Who uses this kind of technology to write SQL? Joins, like this? Yes, some of you? You're all wrong, think again. This is not SQL, not even the example before was SQL. When I talk about SQL, I always show this slide by Marcus Winand with his permission. Are you still using Windows 3.1? No, so why do you stick to the old SQL standards? SQL has evolved very much over time. This is also SQL, ladies and gentlemen. So in the front row, you can read this probably. You have all mentally processed this, and you know what the result of this query is. It's the Mandelbrot set. So if I zoom in, we see very nicely, you can do this kind of magic with relatively simple SQL statements. How is that? SQL 99 is Turing complete. Not many of you might have known this, but it is a fact. And what does Turing completeness mean? After this talk, if you didn't know before, you know now, you will rock at parties. You can tell everyone about Turing completeness. This is the most important topic to software engineers. And it actually just means any program could be written in SQL, if you're crazy enough to do that. What is the strength of a 4th generation language? Why is it so strong? You tell the machine what, not how. That is the whole purpose of a declarative programming language. You're not saying, okay, do this table first and then join it with that one in that order with a nested loop and then hash joins and I don't know what, and then you add another table and you reorganize the algorithm because you've used an index that is much faster. You just tell the engine, this is the result, do it somehow for me. What do you prefer? What do you think is more modern? This kind of approach? Or that one? Yes, so the 4th generation language concept was a very old one, and mankind has always dreamed to tell the machine what and not do the hard work of actually optimizing things. So this is one of the reasons why the company is called Oracle, because you ask the Oracle and it magically tells you the answer. You don't care how it got the answer. What's the problem with SQL? Why doesn't anyone really like SQL? Or some people do, crazy people like me, but you probably don't. That is the problem with SQL. Everything that's green in this statement are keywords. So you have a lot of keywords, right? It reminds us of the good old days when we used these kind of languages, which were a lot, machine put this over there, and you really write machine put this over there. So the syntax is awkward. That's why people don't like SQL very often. Another reason is declarative thinking is hard. It is not very easy. You have to completely change your mindset. You stop writing loops. You stop writing if, else, or these kind of things and tell the machine, okay, go over there. you declare stuff, but you have to change your mindset when you use SQL. But the reason why you should use SQL is reporting, for instance, is very easy with SQL. Bulk data processing is very easy with SQL. It's much, much easier than if you write out the algorithms. Ad hoc analytics, that's the most easy part. That's what SQL was made for, ad hoc analytics. So you are in front of a normalized schema, you just type the SQL, you have never done this kind of analysis before, and it just works. So ad hoc SQL is very easy with SQL. And by very easy, I mean hard. But you don't have a choice, right? So Winston Churchill, I have a quote here about Winston Churchill, SQL is the worst form of database querying except for all the other forms. But there is a path forward, ladies and gentlemen, and it's because all of you are equipped with a SQL muscle. This is the SQL muscle. It needs constant training and practice. So you have to practice this stuff with talks like this, then you do exercises, you can answer Stack Overflow questions, whatever is your path, you just have to practice this technology. All of you are using it, you have raised your hands, all of you are using it, all of you have it on your stack, use it, but practice it. So I've recently added another slide because I thought about if this is the SQL muscle, what is the Java muscle? This is the Java muscle, right? You don't use your brains, you use strength, right? You have a very, very, very strong language. This is a typical example of a Java muscle, right? Okay. Enough of the blah blah. What you came here for is something else. You came here for this list. So this is the list of 10 SQL tricks to convince you that SQL is awesome. These are the tricks. Don't take pictures, it's all online. You don't have to remember the exact tricks right now. I just have 10 very nice examples that we can solve with SQL. You might not have chosen SQL in the past to solve these. From now on you will, because it's so awesome. It's actually this awesome, okay? So are you ready for this talk? Because it's a very long talk. I spent a lot of time writing all of these slides. It's tons of slides. I don't even know how to fit it in 50 minutes. And while I wrote all of these slides, I thought, let's thank our patron saint, Eder Lovelace. Because when I wrote these slides, I realized without Eder Lovelace, instead of writing awesome SQL, we would all be writing some PowerPoint or something else, right? So we can code SQL, that's much better. So, trick number 1, let's go. Everything is a table in SQL. This is the boring trick, but I have to put it in there because it's very interesting. So who in here can spot the table? Yes, anyone? You can spot the table? It's right here, exactly. Who in here thought that this is the table? That is also the table. I told you everything is a table. If you put this, for instance, in a from clause, you can still use this as a table. Everything is a table. This is called a derived table. If you put the table in the from clause, if you put a select in the from clause, you can also do these kind of things. You can do ad hoc tables, in-memory ad hoc tables, like with this values clause. So that works in SQL Server and Postgres, for instance. And then you can rename all the columns of this table with the derived column list. So in this talk, I often show the dialect that actually supports this feature. Often these things are not supported across all the dialects, but this is a SQL standard. It might even show up in other databases. So this is the values clause. You might know me from statements like insert, right? So the values clause in insert is actually a table. You're inserting a table into another table. When you think of this values clause, how Oracle supports it, it doesn't. It helps you type more, keep your fingers busy. So Oracle is also more in the muscle area of the SQL, but this is the same thing. You have this kind of in-memory table for Oracle, and you see the select, you can also supply that to an insert statement. Insert select, so you're inserting one table into another table. It's very interesting to think of SQL this way. Everything is tables. Because SQL is a set-based language, so the origin of SQL is relational algebra, which is a set-based theory, where everything is set. So the difference between tables and sets, most importantly, is that tables allow duplicates. In Postgres, even this is a table. So every function in Postgres is a table. It just happens to return one by one column, one row, one column. You can use everything in Postgres as a table and join things. It's extremely interesting to think of SQL this way. If you compare it to Java 8, so on the left side we have SQL, on the right side we have now the Java 8 Stream API. Think of things like this. Think of sets. Think of data collections. Don't think of the individual rows, which are the tuples. Think of the whole thing. So in SQL we have tables, in Java we have these streams. It's more or less the same thing. Everything you do with the stream generates a new stream. In SQL, everything you do, like a select, generates a new table. You just don't see it with the syntax because you don't have that type written nicely like in Java or in other languages, but they have SQL and the Stream API have a very close match. you can actually, we have a blog post down there in our company that compares these more thoroughly. And if you're looking for better streams with more features that are more like SQL, we have this library, short advertisement about Lambda. We add more features that are in the sense of the SQL mindset and also other programming languages to the Stream API. It's open source, so try it out. So you can do things like these. That's a very simple example where you collect more than one aggregate function at once and you get a tuple back. So that's chapter number 1. Trick number 1, everything is a table. Everyone is still following. This was the boring and easy trick. Now it gets harder. Promise you, this will get hard talk. Second one is data generation with recursive SQL. So common table expressions, also known as subquery factoring in other databases like Oracle, or just the with clause, they're the only way to declare variables in SQL. So this is how it works. We have this with clause, and with the with clause, you can declare variables that are tables. It's very simple, actually. So this T1 table is a table, and it is declared as being just one row with 1 and 2. The T2 table is also a table, and it can refer to T1, so these variables can refer to each other. And finally, at the bottom, you can just use all of these tables in your SQL statement. That is very easy to understand. It's very useful when you have a big problem. You do a divide and conquer approach to the problem. You first solve a very small problem with a common table expression, then you add another common table expression, and so you can easily write a huge query in a very understandable way with variables, right? So there are a couple of caveats with common table expressions in terms of optimization. This depends on your database engine. So sometimes you have to really be careful, check out the execution plan. What's really interesting about common table expressions is they can be recursive. And this is a recursive common table expression that you see here. As you can see, it is recursive, right? Yes? I stole this lame joke from Hadi Hariri from JetBrains. Credit where credit is due. I really loved it for recursion. Anyway, how it works, if you go back, we have this. The recursive keyword is just optional in some databases. In Postgres, it's required. We declare T as being a table or a select with a union all in it. That's the syntax requirement. And then the first subquery of union all is this recursion seed. So this is the first row. It's like a constant. And based on this constant, you recurse in the second subselect. And you can see this here. The second subselect selects from T. But we are about to declare T. So we're using the T name, the variable of the table T, within the declaration of T, recursively. So the first row is just 1, and then the second row that we concatenate with union all is 1 plus 1. And it also selects from T, so it goes on and on and on. It just concatenates the next value. This is just the syntax. Whether your database implements this as an iteration or as a recursion is up to the database. Sometimes it performs, sometimes it doesn't, depending on the database, but it's very, very useful to generate a series of data like this, ad hoc in memory. This is the syntax for Oracle. Oracle is the second syntax for the same thing with connect by. For simple iterations, this is simpler in Oracle. For complex iterations, as we're going to see later on in the talk, you're probably going to use with instead of connect by. So now if you look closely, this example again makes sense. It makes total sense. If you zoom in, you can see with recursive, so the Mandelbrot set is the prototype mathematical example of recursion. So how is it defined, the Mandelbrot set? You don't have to mentally parse the exact SQL, but the point is that we, for this area that we generate, x and y, on each spot of the complex number space, we recurse for some formula. And if the recursion converges, then we have a white, I think, or no, it's black in the middle. And if it doesn't converge, if it diverges, we have some sort of color. That's how it's defined. Very beautiful. I have put the link. You can check out the blog. This guy blogs about these kind of things. He also paints snowflakes and stuff like that in SQL, everyday use cases, right? So, what are everyday use cases of this? Iterations, that's an everyday use case. If you have to generate all the dates in July 2016, for instance, if you do a report, and you don't have those dates necessarily because it's something like login data, but on Sunday no one logged in, but you still want to have the Sunday in the data set, you can just generate these data sets like this. Or generating graphs. So sometimes if you have something, a graph problem in your database, and you don't have many graph problems, so you're not using a graph database, you can just do 1 or 2 queries with SQL to generate graphs in SQL. It works. Still everyone okay? Trick number 3, running total calculations. What is a running total? You can ask your product manager to give you a crash course about the awesome, everything is awesome in this talk, awesome Microsoft Excel, and he will tell you, okay, just do this little calculation, these two columns, you subtract them, and then you take the crosshair cursor and you run through your spreadsheet, and then you get the running total. That's a very easy explanation of what it is. So we calculate that with SQL. Why wouldn't we not calculate that with SQL? So first, a little theory to explain you how to do that with window functions. Who in here has already heard of window functions? Very few. So you're already in trick number 3. You're already lost, right? So you're learning a lot of new things today. It's really awesome how you can do that with window functions. There was SQL before window functions, and there was SQL after window functions. In my opinion, this is the most important step towards more modern SQL. It's a brilliant invention, and it's very concise. In functional programming, you would write that completely differently in a more composable way, but in SQL for ad hoc reporting, this syntax is actually often preferable to functional programming. So what are window functions? Window functions are aggregations or rankings on a subset of rows relative to the current row being transformed by select. Oh my God. It's a very complex concept, but it's actually very easy. After this talk, or if you read up on it once more, I suggest strongly you do, you will see a very, very powerful feature. Window functions are a function with an over clause. So the function calculates some sort of aggregation over a window of your data set. So you can reduce your data set to this window and then do that calculation. And that window can be defined with 3 clauses that we see here. The first one is the partition by clause. So whenever you're selecting something, we see here on the right, we have a movie database. So we have titles and lengths of the movies, of the films. Now, when I do some sort of calculation with a window function, I first declare the partition. And the partition is all the rows that have the same value for length as my own row, as the current row. So all of these films that have length 46 will be in the same partition, or like a group by. So this is one partition, this is the next one. So we look at these partitions individually. That's the first clause. The second clause is order by. The partition, each individual partition is ordered independently from the query that you're writing with this order by clause. So here I ordered by title. As you can see, the titles are ordered ascendingly within the partition, but individually for the partition. So the other partition and the second one, they're ordered independently. That's the second clause. The third clause tells me I want to just consider the rows between so many rows behind and so many rows ahead within the ordered partition, right? So I ordered the partition, and now I say within the order, I want to go, for instance, 2 rows ahead and 2 rows behind. And now that I have defined this window of 5 rows, ordered rows within the partition, I can do some sort of function. Like in this example, I just calculate the row number. This is a ranking function, very easy. And I get 1, 2, 3, 4, 5, 6, 7 within the ordered partition. And the other partition also has its own ordered row number. Let this settle a bit. This is a couple of keywords. You might think, what is this useful for? Okay, row number, right? So you would do that in Java very easily, just the index of the array. But this is extremely awesome. So window functions are aggregations or rankings on a subset of rows relative to the current row that you're currently selecting. So every time you write select, you have a row. And within that row, you can access all the other rows on top or on the bottom and do an aggregation on that. So back to running totals. This is the database table. So we have value dates and amounts. That's kind of like a bank account transaction table. And we want to calculate the balance on each row. We've seen that in Excel before. The formula would be more or less like this. So on row number 4, we have a balance. And you can calculate this top down or bottom up. It doesn't matter in maths or in the formula. I'm calculating it top down, so I know the top balance in some other system, some accounting system. I subtract all the amounts that are above of the balance that I want to calculate. So I calculate balance number 4, which is balance number 1 minus amounts 1, 2, 3. Right? That's the formula. You would do that like this on an Excel or if you write it like that. That's the window function. So you do sum of amount. So you sum these amounts over the window that is partitioned by the account ID. So you don't want to have your neighbor's bank account, only your own. So for every calculation, you consider only your own partition, your own bank account. Then you order this partition by validating ID. That's how you order bank account transactions. And then you say, I want to go an infinite number of rows behind until one row behind. And that is your window. And over this window, you calculate the sum, and you have a running total. And this is extremely fast because it all happens in memory in the database. The database has already loaded all the bank account transactions, and now in memory it can calculate this stuff. And actually, the database does optimizations because it realized it's a sliding window, so it can just sum up the current amount to the sum that it has calculated previously. So it doesn't even have to go through the whole window at every iteration. So this is extremely fast. You can work with this in all commercial databases and in Postgres as well. It's a SQL standard as well, like common table expressions. So these are the tools. In this talk, we have two tools. Remember this tool set. We have recursive common table expressions and window functions. Now it gets really interesting. Now that we have the tools, we do the really interesting stuff. You know this? Ever seen this? Okay. So don't worry if this is a bit fast, if this is how you feel. Experience comes with practice. Remember the SQL muscle. You have to practice this, but window functions are what you can use every day. Even this row number, this is so easy to use. It's very practical. Trick number 4, finding the largest series with no gaps. So this is Stack Overflow, a very nice example. Stack Overflow has this batch system where you get rewarded really, really important things, so you can show off your batches. I have millions of batches, for instance. I'm so good in Stack Overflow. So this particular batch here, the enthusiast and the fanatic, they work like that. So enthusiast, if you go to the site for 30 consecutive days, you get enthusiast. 100 consecutive days, of course, I have that as well. I don't care about wedding dates and other sorts of birthdays of my wife, so I have the fanatic. And how do you calculate that? So these are, for instance, the login times, right? So we don't care about the timestamp, so we just calculate the login date first. That's when I logged in. So I do that with a distinct and a cast. I upcast timestamp to dates. That's very easy and trivial. So that's how I get the login dates. Now I do a row number calculation. I enumerate all the dates within the data set, 1, 2, 3, 4. We know that as well now. It's just row number over this window ordered by login date, right? So this is how we get 1, 2, 3, 4 in our data. And now what happens if I subtract the row number from the login date? If you have a reasonable database, which are most databases, if you subtract an integer from a date, you get another date, because the integer then is considered to be the number of days. That's very useful. So we get these days, and you see 14 minus 1 is 13, 15 minus 2 is 13, and then suddenly you have this gap. So when we have a gap, you all see the gap visually in your brains, because we're humans, we can see these kind of things, but the machine needs an explanation. And you see the gap on the left, we also have a gap on the right, huh? That's interesting. So consecutive row numbers. Wow, okay, that's an easy explanation for this, is the row number never has any gaps. It's a continuous series of integers with no gaps. That's how row number is defined, but our data has gaps. So whenever I subtract a gapless series from a gapful series, I will have the gap again there where the gap was. But now you see all the dates that don't have gaps are the same, so what I can do is just group by this virtual date. I don't care about the date value, I just group by it, take min and max, and I have the result. So this is the longest series of consecutive dates. I'm still far away from any batch. I have 3 days in a row that are in my data set, right? So that's a very easy trick. This is the SQL statement. It's rather easy. I hope you agree with this. It's hard to come up with the idea, of course. It's hard to think in this way. It's hard not to write this loop and remember all the local variables and whatever. But I've just declared this, and the database calculates it very easily for me once you have gotten used to the syntax. So it's really, really easy, right? You all agree. Okay, trick number 5, finding the length of a series. So I really have to squeeze this into the time, so I'm going fast. Sorry for that. You can watch it online later. Again, and see the slides. Finding the length of a series, in this example, is a bit more tricky. So this is a series of bank account transactions, and I want to find the length of these series. So these are the lengths. Anyone see what the series is? Can anyone mentally detect what I'm calculating here? Positive, negative, exactly. So I'm just calculating how many times did I have a consecutive positive amount and how many times do I have a negative one. So I have 2 positive ones here, 3 negative ones here, 2 positive, negative, positive, right. So that's the series, the length of the series I want to calculate. How do I do that with SQL? First, I calculate the sign. That's the interesting part. I don't care about the amount anymore, just the sign is interesting. So this is 1 and -1. And once more, these row numbers, they're so useful. I'm just doing that again. So I have the row numbers from 1 to 9 here. That's easy, right? That's the easy part. So just sign as sign and row number ordered by ID. So now that we have this data, we want to calculate low and high values. What are these low and high values? So low means it's the top value of the series or the lowest value of the series, and then we put the row number in it, right? So that's the beginning of the series, and we put the row number in low, and at the end of the series, we put the row number in high. Why do I want to do that? I will resolve that right after, but this is what I want to do. So for instance, in this series, we don't have any row number 4, we don't care about 4, we just have 3 and 5. 6 and 7, 8 and 8, this is the same value for both values because the series has length 1, and 9 and 9. How do I do that? Again, with window functions. They are the incredibly useful lead and lag window functions. So here we have values class, right? So we generate the table with values 1 to 4, and then we use the lag and the lead value when we calculate this table. So on here, I'm going to use this wonderful Microsoft PowerPoint laser pointer that is, it never works. Oh, so it's also on camera. So here we have the values row with values 1, 2, 3, 4. And on each row, for instance, on this row, the lead value is 3 because 3 is the next value. You see follow the arrow here? So we take the next value and put that in the same row here. The lag value 1 is the one that was previous, and we put that in the same row. So lead, it takes an optional argument. We can say, okay, just 2 or 3 or 4 rows ahead and behind, and by default, it's just the next row. Lead and lag, very, very useful. So this we're going to use very easily with a case expression. So when lag of sign, so when the previous value of the sign was different from the current value of the sign, then we put the row number in row, right? So that's the beginning of a series. The beginning of a series is when the sign switched. So the previous value is different than the current value. The next value of the sign is different from the current value of the sign. That's when we put the row number in high. And of course, we do some null mingling because SQL is a very null-affine language, so that's boring. We know how to do that. So we have low and high, but we don't want to have low and high only at the beginning and the end. We want to span the value over the whole series. That's what we want to do, really. So how do we do this? You see here, in the first series, 1 and 2 is in each row. 3 and 5 is in each row, again and again. So how do we do this? I'm using here a syntax that is not supported by all databases. It's supported by these databases that have more analytics functionality. It's a syntax that uses ignore nulls. So this is a bit complex. A lot of keywords I told you, but once you get used to the keywords, they're extremely useful. So ignore nulls, as you can see here, ignore nulls, it just removes all the nulls from the window. It's a very useful feature from every now and then. So now we take the low value and we still order everything by ID, and we go as far as we want behind until the current row, removing all the null values. The same with the high value, and I'm going to show visually afterwards how it works. It's probably simpler than with keywords. So again, we do some null handling, and what we get is this here. So when we look closely at this slide, when we want to calculate this value here, this one, on row number 5, we consider the whole window that is on top of it. So all the rows on top of it, and we take the last value on top of it, which is not null, so that goes up to here, right? On row number 3, when we take the new high value, we take the first value that is on the bottom of it, except for all the nulls, so we go down to here. So that's the first value we encounter. So first value and last value, like lead and lag, take just the first and the last value from a window when you order it. That's very, very useful. So when we execute that, we get this result. Now that we've done this, the final step is just a bit of math with off by 1 error handling, right? So 1 plus high minus low is the length, and that's how we get the result in SQL. I personally find this pretty and awesome. It's a lot of keywords. You wouldn't write it like this. You would probably optimize this, but it's a very nice example to explain all these window functions step by step. So I first take the data, generate signs amount, a sign of and the row number. Then I do this low and high mingling 2 times, once just for the beginning and the end, and then once for the whole series, right? Does that make any sense? You still okay? So this is an advanced SQL talk, I promise you, but it's a very useful talk. I think a lot of these features are already in your database. You run that in production, you just have to use them. So this one is a funky problem, so subset sum problem in SQL. No one would do that, right? But why not? There's an explanation on XKCD. I can't show it here because of the non-commercial license. I mean, obviously doing commercial talk, so can't show it. Look it up. It explains the subset sum problem. There's a boring explanation on Wikipedia, and I have an easy explanation for you right here. So subset sum problem means these are sums, or these are target values, and for each of these target values, you want to calculate a sum of a subset of these items, right? So that's a very easy problem. All of you have mentally processed this already and came to the conclusion that this is the solution. These are the closest sums that you can form from these items to get as close as possible to the total, right? It's not an easy problem. The naivest algorithm is exponential. I'm going to show that one. There's a more optimal algorithm that's approximative. It's a polynomial, but it's harder to explain. I'm going to just show this one, which is exponential. There are 2 to the power of n possible subsets among the set of items. That's why it's exponential, right? So how do we do this? We just write a common table expression, and then we select something, and then we draw the rest of the all, right? Who feels like this? Who would solve this with SQL? Probably not. But you can, and you should. So what are the possible sums? I'm just going to quickly explain the algorithm. So the algorithm is rather easy. We take these 10 single item sums. So all of these items by themselves are already a possible sum, right? You just take one of the items and put them on some stack, some conceptual stack. I have 7,120. That is one sum. And I can form many, many more sums by combining this sum with the remaining sums. I use this writing style here, so I calculate the sums of the indexes 2 to 10. So for instance, this is also a sum that is possible, right? That shows the second item, first and the second. That's a sum, and I can combine this sum with all the remaining sums in the set of sums. I can also skip items, so I can skip 3 items, take the item number 1 and number 5. That is a sum. I combine that with the remaining sums. You can see immediately why it's exponential, because for each item, I can just say 1 or 0 if it's a part of the sum or not, right? That's the algorithm. It's naive, very simple, and it's exponential. So how do I do that? I calculate the possible sums with recursive SQL. So here I'm not using the recursive keyword in Oracle because it's not possible. It's just always recursive if you want. So I'm calculating a table that contains all the possible sums. That's the table sums. And in this table I have 3 columns. The column sum is the sum. The column ID is the highest ID I have used for this sum. And calc is the calculation string, so the formula how to get to the sum. In the first iteration, as we remember, I use this recursive style. So the first iteration is just taking all the items and putting that in the table again, right? That's easy. Those are all possible sums. Now from the first item that I take, I recurse with union all. And then I write this very simple SQL here. It's not hard. So how is it defined? I select again from sums recursively, and then join the items again. So at every recursion, I join all the items again, and I take all the items that are bigger than the last item that I've added, right? So in the conceptual slide, I take only the items that are below the ones that I've already considered. That is how you calculate all the sums. And the individual sums are here. So this is a sum. The first sum is just the item. The second sum is the previous sum plus the item, or the item plus the previous sum. The highest ID is just any ID. So every time I add an item, I take its ID. That's the highest ID. And this calculation formula is just the concatenation of the previous items with the plus sign. That's how I recursively generate this string. So that are all the sums. Now I have to get as close as possible to any of these. I will have to find among all the sums for each of these totals the closest total. That would be this query. So we're looking at the line here with the min and absolute value. I'm using a cross join to combine all the sums with all the totals, or all the totals with all the sums. And for each total, I group by the total and I find the minimum absolute value of the difference of the total and the sum. Right? So the minimum absolute value would be the best difference. So for each total, I have found the best difference. That's not really what I want, but it's one of the ways how to calculate this thing. So if you're not sure what cross-join is, a cross-join in a relational algebra is a Cartesian product, is the same thing. So it's just if you have a deck of cards, this would be a cross-join among the ranks and the suits. So you combine all the ranks with all the suits. That's a cross-join. Very useful for these kind of reports to know cross-join. You can also just have a comma separated list of tables in SQL. But it's nice to have a keyword and you can read it better this way, if you see that it is a cross-join. Now, I really want to have the sum, so here I'm using Oracle syntax. I don't want to have the difference, but the sum. I'm not going to explain the syntax in detail, it's just within a group. So for each total within the group of sums for that total, I'm finding the best value for this absolute difference, and I get the sum. So you can try this on your Oracle instance. If you have Oracle, who is using Oracle? So you have all of these features. Oracle is one of the most reporting feature-rich database. You have this query here. It's all you need to do for the subset sum problem in Oracle. You're feeling like this, right? Electrified. I have to speed it up a little. So trick number 7. Capping a running total. We've seen running totals, now we want to cap it. So whenever we go below 0, so for instance on row number 4 we have this instance where we have a value that is lower than 0, we want to keep 0 as the value. That's like capping the running total. We never go below 0. So conceptually we would just take the greatest value of 0 and the actual sum at that point, right? So with Microsoft Excel, again you would just put the formula in the cell, drag and drop, tear it down, and then you have something like an if statement. If it's below 0, then take 0, and if it's not below 0, take the sum. How do we do that? So everyone knows Microsoft Excel is the first popular reactive programming application, right? So if you follow the buzzwords, everyone talks about reactive programming, it's an ancient thing. It's what happened a long time ago in SQL. When you update one cell, the whole spreadsheet updates reactively. So how do we do reactive SQL? How do we do it? With window functions? It's probably not possible. It's very hard. It's maybe possible. I'm not going to explain it here. With recursive SQL, it's not geeky enough. So how do we do it with obscure vendor-specific SQL? Yes, of course. Someone else will maintain it. Yes, you're all like this. You write this report, then we leave the company. Next poor developer will have to come up with reading this whole thing with Oracle SQL. So we have in Oracle the model clause. The model clause is extremely powerful. You just put model after any table, and then you have a spreadsheet in your database. So this spreadsheet works like this. I'm only explaining the very simple clauses, not the complex ones. The other talk already finished. It's still 15 minutes, right? About join, you will learn the awesome part of the SQL stuff, the Oracle vendor-specific stuff. Okay, spreadsheet works like this. So we have the dimension clause. The dimension is in the spreadsheet, like in Excel, X and Y, right? These are the dimensions. In Oracle SQL, you can have as many dimensions as you want, like 11 dimensions if you do some string theory math in the database. Then you have the measures clause. The measures are what is inside of a cell. In Excel, you only have one value. In SQL, you can have a tuple in the cell. And then you finally have the rules. So in Excel, you put the rule in the cell. In Oracle, you just have a list of rules that apply to all the cells. And Oracle resolves them for you. This is how we start doing it. So we have the amounts table, and we add the total value as 0 in the beginning. So for every transaction, we have a 0 value initially. And then we model. And we have this dimension first. We dimension by row number because row number is consecutive without gaps. That's perfect for dimensions. We have 1, 2, 3, 4, 5 to address each cell. Then we have the measures. Each cell has 3 values. And then finally we have the rules. It's only one rule. And the rule is, with this syntax, for any value of the dimension, so for any cell index, we take the greatest value of 0. And this CV syntax, CV means current value, so we take the current value of the row number, so the current index, minus 1. So we take the total value of the row above, plus the amount of the row next to it. So this is exactly like Microsoft Excel. It's a bit funky, the syntax. Every time I do this, I have to read it, so every time that means once a year, all right? So when getting nulls right, again, this is boring, I don't explain this, but ladies and gentlemen, this is reactive SQL, that's the future. Reactive SQL in the Oracle database. You can read the white paper here, just Google Oracle model white paper, and you will find a very nicely explained white paper that explains all the features of model. It's not hard. Of course, no one can remember this, so you always read the white paper, but once you have this kind of situation, you can very easily solve these things with model. Okay? Time series pattern recognition, trick number 8. Oh my god, okay. It's a very fast-paced talk, and this one is very complex, and I'm going to explain it quickly, as all the other ones. But it's very useful to you if you have Oracle. I'm going to show you how to do this kind of calculation. So here we have, again, lengths of series. We know how to calculate these. We're not really calculating this one. It's just conceptual, the length of the series. And we want to generate this kind of trigger. So imagine your fraud detection system or some sort of a data mining system in real time or something like that. You want to have a trigger when something happens. So here we have the trigger on this row. Why on this row? It's just the business rule that I came up with, because that's how I imagine things are in these businesses, right? So trigger on the third repetition of an event if the event occurs more than 3 times. That sounds weird, huh? You have to remember 3 times before and at least once afterwards, and then trigger something. How do we do it? Again, right? So we have, again, our mindset. We know we're using Oracle, and we're using Oracle Match Recognize in this situation. If you have Oracle 12c, that's a new feature they introduced, Match Recognize. It helps you doing pattern matching in the database, in time series. That's really awesome. They make tons of money only with this feature. So how does it work? Match Recognize has these clauses. First clause is order by. So for some reason here you have to put parentheses, whereas in model there was no parentheses, so again, SQL syntax, right? But order by is the order of how you match the rows. That's easy. Then the measures is, again, what you want to have in the results, like in model, so the kind of the cells of each result. Then you want to return all the rows per match, right? So you can also select only a summary of each match. Then here is something like a regular expression that you want to match. So when you do matching, you always use regular expressions. They're really powerful for matching, also in strings, so why not here in the database? And here you define what is an event. So what is the event you want to match? Are you ready? Okay, no, you're not. But I'm still showing. This is the result, I put that up here. So I order by ID, right? So that's easy. Then I take this classifier function. That's just a function that returns the rule that I put in define afterwards. That's why I'm just doing it this way. I want to have all the rows per match, so I want to retain the rows. Then here is my regular expression. I'll explain afterwards. I'll explain now. It's a start event, a repetition event, then the trigger X event, and then at least one repetition event again. And the second part is optional. If I don't have the second part, then I start again. I start the next match. Right? So if I don't have the repetition, X repetition, I start the next attempt. And here are the rules. I define R and X as being the same thing. R and X are just the event that the sign of the amount is different. No, it's the same as the previous sign of the amount. So a repetition is the sign is repeated, right? And X is also a repetition, but a special repetition. So this is the whole query, and that will return this result. So if we go from bottom up, we see S, we start a new match. But RXR doesn't happen, the sign changes. Here we have 3 times started because RXR doesn't happen, right? So we assign S. S has no definition, so S is all the rest. Here we have a match because SRXR matches. That's the regular expression of our defined events that matched. So we put these classifiers on each row. Now finally, just remove all the boring classifiers. We only care about X, so we remove S and R, and we get the result. Now, if you're not like, shut up and take my money to Oracle, then I don't know what. This is really awesome. It is pattern matching for time series in the database. Again, if you have Oracle, just read the Oracle Match Recognize white paper, Google that, and you will be you will not be disappointed. So I have to speed up. 5 minutes left. Okay, now that you're experts, this trick number 9 is almost too embarrassingly simple. I want to pivot and unpivot in the database. So here we have actors and films. So here we have actors, film titles, and the ratings, which mean at what age can you watch the film. And if you want to pivot, you might want to do something like this, kind of like group by, and then count the number of films per rating, but you don't want to have them in rows. You want to have them in columns. That's pivoting, right? In Excel, you have a pivot table as well. So this is pivoting, and this is unpivoting, back to rows instead of columns. That's too easy. In Postgres, you would do it like with this filter clause. So each aggregate function has this optional filter clause. You can just say, I want to aggregate only these rows per group that fulfill the predicate, right? So for each column, you do a little typing, it's always the same thing. Very useful. If you're not using Postgres, you have to type 2 more characters, as you can see here, with the case expression, because aggregate functions, like count, they don't count the null values. They only count the real values. So if you remove all the values that you don't care about and turn them into null, you don't count them. That's how you pivot. If you're using one of these databases, Oracle or SQL Server, you have the nice pivot clause. It's like the other clauses before. You just put that after the table, and then you can list a number of aggregate functions for a number of values in a list. So that's how you pivot. That's how you unpivot. Remember, it's possible. If ever you have this kind of transformation, and if you have one of these databases, it's very easy with the syntax. Pivot and unpivot. So pivoting is taking values from a single column to become multiple columns, and unpivoting is the opposite. That's too easy. Now the final topic, last trick, abusing XML and JSON in the database, because why not? First, a word of truth. A word of truth, ladies and gentlemen. You have never heard this before. I'll tell you today, JSON is just XML with less features and less syntax. You all agree. And you also all agree that XML is awesome, right? Now, because JSON is less features and syntax than XML, the corollary of this is JSON is also less awesome. So this means we don't have to treat JSON in this talk, we just talk about XML, and by the way, XLT is the only thing even more awesome than SQL. You all agree to that. So, no kidding, I'm actually serious. How do we do this? So we have here a list of films and actors. We want to get to this denormalized table form, right? So you see the films are comma-separated list of values. How do we do that with SQL? We now know all the tools. We just do recursive SQL with these 3 steps. For step number 1 is we parse the XML in the database. This is Postgres syntax, just double colon, cast the thing to XML. Then we do some XPath magic. So we just extract all the first and last names and the films from the XML documents and turn that into columns. That's very easy. And the final step is we just do a little bit of regular expression recursive magic. So we pattern match recursively until we don't find anything after a comma anymore. And that's how we're done, right? So I love geek and poke. This applies very nicely to this example. 10 SQL tricks to convince you that SQL is awesome. These were the 10 tricks. You can't say awesome without saying awe, and awe means in English a feeling of fear and reverence. You all agree? You're all amazed as well, so it's a feeling of amazement. I like amazement because you can say amazement without maze. And what does maze mean? Maze is a labyrinth in English, a puzzle consisting of a complicated network of passive messages. I like the third definition, confusion of thought, perplexity, uncertainty, but most important is state of bewilderment, and you can't say wild. Okay, we stop here. Why do I talk about SQL? SQL is the only ever successful mainstream and general purpose 4th generation programming language, and it is awesome. All of what I've shown today was declarative. You didn't write one single algorithm, you just told the machine, this is how I want to have the data. Why doesn't anyone else talk about SQL? I don't know. Really, it's so awesome, no one talks about SQL. Now you're all like, can I do SQL in Java? Of course you can with our product. Juke is our product. We do SQL as an internal domain-specific language directly in Java. So every keyword is a method, every table is an object, and you have type-safe SQL compiled by your Java compiler. I can't talk too much about this today. Google it and look it up, juke.org, and then be amazed once more. So what's the key takeaway of this talk? What do you take away from this talk? Can you do it in the database? Yes. Right? I've proven it. It's Turing complete. You can. Can you do it in the database? Yes, now you can. You know all the tricks. And if that was too fast, I have a slower version of this talk. It's a 2-day SQL training that we're offering. And trust me, you will be able to follow. It's much, much easier, much simpler, but as deep as this. So these are awesome SQL features that you all have in production. Can you do it in your database? Yes. Most of you raised your hands back then, unless you're doing MySQL, because MySQL can only do trick number 1, right? Everything is a table. Should you do it in the database? No. I'm just kidding. Of course you should. Of course you should. Do listicles attract attention? I would say yes. This is a Java conference. The room is full for a SQL talk, so 10 SQL tricks does attract attention. Will this talk ever end? Also, yes, ladies and gentlemen, thank you very much. These are my coordinates. Please do get in touch.